Good morning. In today's lecture, we will discuss about the boundary conditions of electric and magnetic field. Before going to this topic, we have discussed about the boundary conditions in electrical field and magnetic field separately. Now this is related to the combination of both electrical and magnetic together. So under this we have four different conditions. The first condition of boundary is the tangential component of the electrical field is continuous at the surface, which means that the field outside the surface which is similar to that of inside the surface. The second condition is tangential component of the magnetic field is continuous across the surface except the surface of the perfect conductor. This is differentiated between your electric and magnetic field. Since at the surface of the perfect conductor, this tangential component is equal to some amount of current density. You call it as a linear current density. Next, coming to the third condition, the normal component of your electrical flux density is continuous provided that there is no surface charge density. Next, the normal component of the magnetic flux density B is continuous at the surface. So these are the four different conditions of boundary. Now we will consider a rectangular box. Onto the rectangular box, left side we have the medium 1 and right side we have the medium 2. So we classify the electrical field with representation of E and magnetic field with representation of H on both sides of the medium. E1, EX1, HX1 resembles to the medium 1 and HX2, EX2 resembles to the medium 2. Coming to the y-axis, EY1 and HY1 resembles to the medium 1 and EY2 and HY2 belongs to the medium 2. And coming to the below portion, EX3, HX3 belongs to the medium 1, EX4 and HX4 belongs to the medium 2. This rectangular box consists of a length of del y and width of del x. Okay. Now I am considering the integral form of the second Maxwell's equation, that is E dot dl is equal to dou b by dou t to the surface integral. This condition is supposed to be used into the rectangular. On using this condition, I am writing the equation for the rectangle as Ey1 del y and Ex1 del x by 2. On going to the picture, this del xy by 2 represents that the entire length of the rectangular, that is the entire width of the rectangular is del x. Ex1 consists of del x by 2 and Ex2 consists of del x by 2. So the del x is divided between Ex1 and Ex2. That is why it is considered as del x by 2. But when you take Ey1, the full length del y is considered. This portion is considered. Okay. Next, similarly for the medium 2, the thing is that when medium 1 is positive, medium 2 will be of negative sign indication. Now completing the left hand side of the equations, the right hand side of the equation, what we have in Maxwell's equation is dou b by dou t. Instead of ds, I can write it as the surface integral with del x and del y. Now this is my equation. Suppose in case if I shrink my rectangle, then my del x portion disappears, which means that del x tends to 0. On substituting this condition into that equation, I obtain the equation as Ey1 del y minus Ey2 del y equal to 0. The reason is that right hand side also we have del x, so the right hand side portion entirely becomes 0. Now bringing to the left hand side of the equation to the right hand side, it becomes Ey1 is equal to Ey2. This shows that your tangential component of your electrical field is continuous. Now I am considering the integral form of first Maxwell's equation, that is H dot dl is equal to J plus dou b by dou t to the surface integral. Now applying this equation to the rectangle, the left hand side of the equation of the rectangle shows this. Similarly, field multiplied with the length of the rectangle. Similarly, the field multiplied with width of the rectangle is considered as like the previous condition. Also, del x is divided between hx2 and Hy2. Okay. Next, on right hand side also we substitute the same thing. Instead of ds we substitute del x and del y. Similarly to the previous one, when we shrink this rectangle, del x tends to 0, which shows that hy1 del y minus hy2 del y is equal to 0. Now hy1 is equal to hy2. This shows that the tangential component of your magnetic field is also continuous. Okay. Now we have a condition that the tangential component is continuous across the surface, but except at the perfect conductor. Since at the surface of the perfect conductor it is equal to a linear current density. In case if it is equal to linear current density, the right hand side of the equation J will be present. So we can copy the similar equation of the rectangle now. Here the J will not tend to 0 since it is a perfect conductor. A linear current density is present. So on right hand side we have J, that is a current to the length del y. So this is written on the right hand side. Left hand side equation is hy1 minus hy2, and right hand side your J is present, that is linear current density is present, that is equal to JL. This shows that the tangential component is discontinuous if the linear current density is present in case of a perfect conductor. Okay. Next we will go to the third condition. Before going to the third condition of the boundary, I am considering a pillbox representation. This pillbox, it consists of a volume dV. Instead of dV, it can be written as ds, that is surface area, into del x. Both are similar. So onto this pillbox, I am considering the medium 1 on top portion and medium 2 on the bottom portion. So for this, the normal component dn1 on medium 1 and dn2 on medium 2. Now I am considering the equation 3 from Maxwell's. That is, from Gauss law we have obtained surface integral of d dot ds is equal to triple integral of rho dv. On applying this equation to this pillbox, I am obtaining the equation as dn1 ds minus dn2 ds is equal to rho. Instead of dv, I am writing it as ds dot del x. When I shrink this pillbox, my del x tends to 0. So my right hand side of the equation becomes 0. Bringing the left hand portion of the equation to the right hand side, my equation becomes dn1 is equal to dn2. This shows that the normal component of D is continuous under this condition when there is no surface charge density. Okay. Next, in case of a perfect conductor, which means that there will be some amount of charge present. So in that case, rho is considered, which shows that my equation dn1 minus dn2 will be equal to some amount of charge. Even though when del x tends to 0, the charge will be present. This shows that the normal component of D is discontinuous in the presence of a surface charge density. Now I am considering the integral form of fourth Maxwell's equation B dot ds is equal to 0. Applying this condition to the pillbox, my equation becomes bn1 ds minus bn2 ds is equal to 0. We can bring the left hand side bn2 to the right hand side. This shows that bn1 is equal to bn2. This shows the normal component of your magnetic flux density B is always continuous. Thus, we have obtained all the four boundary conditions. Thank you.